Hi everyone, in this video I will give a review of some of the most popular optimization algorithms for training neural network models. Here is the table of the optimization algorithms that we will cover in this video. I have clustered these algorithms into 5 different categories. These groupings are made based on the similarities of their update equation. I think this type of grouping makes it easier for learning purposes. In the first section, we will start with the basics of the gradient descent algorithm and its variants SGD and mini-batch GD. Then we move to the accelerated GD optimizers, including momentum-based optimizers in section 2, adaptive learning rate methods in section 3, and the Adam family of optimizers in section 4. And at the end, we will see the Lookahead algorithm, which is orthogonal to all those other optimizers. By the end of this video, you will have a good understanding of different optimizers for neural networks and their benefits along with their limitations and drawbacks. Hi everyone. So first, let's understand the basics of the GD optimizer. Gradient descent is analogous to a hiker that is trying to descend from a mountain. So this hiker takes small steps one at a time in the steepest direction until reaching the lowest point. To understand the concept of gradient descent, assume we have an objective function f, which is defined based on a set of parameters or weights, and it returns a scalar output which we want to minimize. In the context of neural network, function f is evaluated on a dataset D, and the output of f is associated with the prediction cost or error of the network, and we want to minimize this prediction cost. Gradient descent is an algorithm for minimizing the cost function f in an iterative fashion. We use t to denote the step number of the optimization throughout this video. So in each step t of the gradient descent algorithm, we can name the current parameters as w sub t, and we want to make an incremental update to these parameters and get w sub t plus 1. In neural networks, we perform a forward pass on all the data samples in dataset D and accumulate the gradients, which are denoted as nabla of f with respect to the parameters w. But for simplicity, we use g sub t to denote the gradients. After obtaining the gradients using all the data samples, the gradient descent will update the weights in a backward pass with this update rule. So w sub t plus 1 equals w sub t minus eta times g sub t. And eta is the learning rate which needs to be determined as a hyperparameter. This process is repeated, so in the next step, we use the updated weights for computing the loss f and its gradient iteratively. Hi everyone. So now let's see what are the drawbacks of the GD algorithm. First, the most important drawback of GD is that in each step, it needs to do the forward pass on all the data samples before making one update. This is very inefficient, especially if you have a very large dataset like millions of samples. A commonly used alternative method that can overcome this drawback is called stochastic gradient descent, or SGD for short. In SGD, instead of having one update per the entire training dataset, we will have one update per each sample in the training set. Another option is to use the mini-batch gradient descent, where in each step t, it selects a random subset of samples from D, which is called a mini-batch or sometimes batch of data for short. And then the loss f and its gradients g are computed for this mini batch of samples. As you can see, with SGD and mini batch GD, we perform more updates compared to the original gradient descent algorithm, and this makes them more computationally efficient. But there is still another drawback of the GD algorithm which we need to address, and that is, throughout the training, some weights or parameters may incur very steep gradients, which causes large updates, while at the same time other weights may observe nearly flat slope. And throughout the training, this may change for different weights, and progress will get slow as some weights approach a flat region like this. In addition, the SGD algorithm and its mini-batch variant add randomness to the updates, so sometimes the gradients may keep oscillating back and forth for some parameters, and this is due to the stochasticity nature of the algorithm. However, now let's move on to the next section. Here we are going to see the momentum-based optimizers. The first algorithm in this group is the Momentum Optimizer, which extends the SGD algorithm using the classical momentum. The update rule for the Momentum Optimizer is as follows. W sub t plus 1 equals W sub t plus M sub t. And this M sub t is the momentum computed as shown here. M at step t is set equal to beta times M sub t minus 1, which is the previous estimate of the momentum, minus eta times the gradients G sub t. And beta is another hyperparameter called the decay coefficient, which can be chosen between 0 and 1, and it determines how fast we should forget about the past gradients. It's important to note that this equation gives us an exponential moving average, or EMA, of the past gradients. To see this exponential decaying behavior more clearly, let's look at the computation of momentum and form their series at different steps. At t equals 0, M sub 0 is initialized to a vector of all zeros. At t equals 1, M sub 1 is negative eta times G sub 1. At t equals 2, M2 is beta times M1 minus eta times G sub 2, which can be simplified as shown here. If we repeat these computations, we can see that at step tau, we obtain M sub tau, which has beta to the power of tau minus 1 times the gradients at the first step G1. So it means the older gradients, in this case G sub 1, has a smaller coefficient than the newer ones. So that's why we call it exponentially decaying moving average. So this was the basic idea of the Momentum Optimizer. To summarize, we covered momentum, which is a powerful algorithm that accelerates training. Some benefits of the Momentum Optimizer is that it can mitigate the randomness effects of SGD algorithm. It also helps in regions where the loss landscape is flat or nearly flat. But now we have to specify two hyperparameters, the learning rate eta and the decay factor beta. Hi everyone, our next algorithm is the Nestrov Optimizer. Nestrov Optimizer uses the same update rule as the classical momentum, so W sub t plus 1 equals W sub t plus momentum at step t. But this new momentum now is an improved momentum. So instead of computing the gradients using the current weights W sub t, Nestrov uses a Lookahead approach, and it performs a partial update for computing the gradients, as you can see in this equation. These gradients that are computed using the partial updates are called Nestrov Accelerated Gradients, or NAG for short. Computing NAG is based on the current set of weights at step t and the previous momentum M sub t minus 1. With these improved gradients, Nestrov has shown to be a very effective optimizer and has outperformed both SGD and the classical momentum. Hi everyone. Now we move to section 3, the group of algorithms that use adaptive learning rates. In this section, we will cover 3 algorithms: AdaGrad, RMSProp, and AdaDelta. Diving into the adaptive learning rate methods, let's start with the update rule for AdaGrad as shown here. As you can see in this equation, the global learning rate eta is divided by a vector which is a square root of v sub t. This scaling results in a new effective learning rate specific to each parameter. V sub t is the running average of the squared gradients. To get an intuition on this effective learning rate, assume a parameter has a history of large gradients. And it does not matter positive or negative since we are using the squared gradients. As a result, the running average of squared gradients for that parameter will grow in magnitude, which then leads to reducing the effective learning rate of that parameter. So that is why this group of optimizers are called adaptive learning rate methods. It's because they adapt effective learning rate for each parameter based on their history of past gradients. The idea of having parameter-specific learning rate is very effective and useful, but there are some problems on how AdaGrad computes the running average of squared gradients. If we expand the equation of the running average at step tau, we can see that V sub tau uses equal weights for all previous and current gradients. This causes a few issues for AdaGrad. First, this makes AdaGrad sensitive to the initial gradients. In addition, this formulation also leads to continual decay of all learning rates. The reason is the denominator is the sum of some positive values, so it will keep growing in magnitude over time. Next, we will see two other methods, RMSProp and AdaDelta, that try to resolve these issues. The second adaptive learning rate optimizer is RMSProp, which stands for Root Mean Squared Propagation. It was first published in a Coursera lecture by Jeffrey Hinton, and it tries to mitigate the issues we mentioned about AdaGrad. The update equation for RMSProp is similar to AdaGrad, except for the way that the running average of the squared gradients is computed. First, let's rewrite the update equation by separating the change delta WT, defined as eta divided by the RMS of the gradients times G sub t. And the RMS of gradients is just the square root of the running average of squared gradients. So up to here, everything is the same as AdaGrad, just a slightly different representation. However, instead of using the regular running average as it was done in AdaGrad, RMSProp uses an exponentially decaying running average. So we have V sub t is beta times the previous squared gradients V sub t minus 1 plus 1 minus beta times the current gradient G sub t squared. Using this exponentially decaying moving average of the squared gradients can help with the following issues. First, it's less sensitive to the initial gradients since when it reaches later steps, the coefficients of the early gradients will decrease exponentially. Secondly, it can also help with the monotonically decreasing learning rates, and this makes it suitable for online problems. Hi everyone! Now we move to another optimizer called AdaDelta in the adaptive learning rate category. AdaDelta also tries to resolve issues of AdaGrad, which we mentioned earlier, using the exponentially decaying moving average of the squared gradients. But in addition to this improvement, AdaDelta also removes the global learning rate eta. Instead, AdaDelta uses the RMS of the history of updates, delta WT, which is the quantity highlighted in this equation. So in addition to the running average of the past squared gradients, we also need the running average of the past squared updates. The computation of this quantity is shown in the red box here, and we use U sub t to denote the moving average of all previous squared updates, that is delta W to the power of 2. Then the RMS of delta W sub t will be the square root of U sub t. So in summary, AdaDelta tries to address the issues of AdaGrad Optimizer, which if you recall, there were sensitivity to initial gradients and the continual decay of learning rates. In addition to fixing these issues, AdaDelta gets rid of the global learning rate. So as a user, we don't need to specify the learning rate hyperparameter eta. However, moving to the next section, here we will see adaptive moment methods or ADAM family of optimizers. So we will start with the Adam method and spend a little more time on that to understand the idea of Adam Optimizer. Once we understand the Adam Optimizer, we will cover the rest of these optimizers in this family. Hi, ADAM stands for Adaptive Moment Estimates, and it has emerged as a highly effective optimizer for neural networks. ADAM is an adaptive learning rate method which adjusts the learning rates based on the first and second moments computed using the exponentially decaying moving average. For ADAM, we must specify three hyperparameters. So in addition to the global learning rate eta, we also need to specify beta 1 and beta 2, which are the exponential decay rates for those two moments. So we use m sub t to represent the estimate of the first moment, and it is computed as beta 1 times the previous estimate m sub t minus 1 plus 1 minus beta 1 times the current gradients g sub t. Similarly, we use v sub t to represent the estimate of the second moment. And note that this is the second raw moment, which means it is an uncentered variance. And v sub t is computed as beta 2 times the previous estimate v sub t minus 1 plus 1 minus beta 2 times the gradients squared. So far, we have seen a lot of cases for exponential moving average of different quantities in this video. This is just another case of EMA, except that Adam has two of them. And the hyperparameters beta 1 and beta 2 must be selected within the range 0 to 1. The recommended values for these two hyperparameters are listed here. After computing the estimates of the first and second moments at step t, next we should apply a bias correction to remedy the effect of initialization bias. So m hat and v hat are the bias corrected moment estimates, which are computed using these two equations shown here. Now we have everything and ready to update the network parameters. So the update rule is w sub t equals w sub t minus 1 minus eta times the current m hat divided by the square root of the current v hat plus some epsilon. This epsilon is just a small constant that is added in the denominator for numerical stability. So in summary, Adam is in fact another adaptive learning rate optimizer which uses adaptive estimates of first and second moments. The benefits of Adam is as follows. Firstly, it's invariant to rescaling the gradients. Also, it's suitable for online and non-stationary problems, and it also works for noisy and sparse gradients. Hi everyone! The next algorithm in this family is AdaMax, which was proposed in the same paper as Adam. So AdaMax uses the estimates of the first moment the same way as in Adam, but instead of the second moment, they use the infinity norm of the gradients. So to follow the development of AdaMax, first let's go back to Adam and look at the second moment. In fact, this is the L2 norm of the gradients, and it can be generalized to LP norm, where P can be 2 or higher. In that case, V sub t would represent the running average of the LP norm of the gradients and is computed using this equation. Now, with this generalized formulation for V sub t, AdaMax lets P goes to infinity, which results in a very simple and stable optimizer. Let's use U sub t to represent the moving average estimate of the infinity norm of the gradients. Computation of U sub t is very simple. It's just the max of beta 2 times the previous estimate U sub t minus 1 and the absolute value of the current gradients. After that, we just need to apply bias correction only to the estimate of the first moment to get m hat, and then the update rule is very simple. So W sub t is computed as W sub t minus 1 minus eta times m hat divided by U sub t. Hi everyone! The third algorithm in this family is AMSGrad, which tries to address the convergence issues of the adaptive learning rate methods such as Adam and AdaDelta. AMSGrad uses the same estimate of first and second moments, but instead of the previous bias correction, AMSGrad simply takes the maximum of all previous and current estimates of second moment V. After this modification to the computation of V, updating the parameters is similar to Adam with this equation shown here. Hi everyone. Our next optimizer is another extension of Adam, which is called AdaBound. The idea of AdaBound is quite simple. The adaptive learning rate methods may result in extreme learning rates which lead to convergence issues and unstable training. AdaBound tries to clip the learning rates dynamically to keep them within a desired range. Using the same estimates for first and second moments as in Adam, AdaBound computes an initial learning rate, which is scaling the global learning rate eta divided by the square root of the estimate of the second moment v sub t. Then AdaBound will clip this adjusted learning rate to ensure that it is within the lower and upper bound indicated by eta lower and eta upper, which can be constant or could be a function of step t. After obtaining the bounded learning rate, which is shown here as eta prime, then we rescale eta prime, so dividing it by a square root of step t, and then we use this learning rate in the update equation. Next, we have AdamW, another extension of Adam that tries to fix the weight decay regularization of Adam. So here, we need a brief background on two regularization techniques, as we are dealing with the L2 regularization and the weight decay regularization. These are two regularization techniques for addressing the overfitting issues in machine learning. Weight decay regularization applies a decay factor 1 minus lambda to the parameters at the previous step. And L2 regularization defines a loss term which is lambda half times the squared L2 norm of model parameters. These are two distinct regularization techniques, but under SGD optimization, L2 regularization is equivalent to the reparameterized weight decay regularization. You can see this equivalence through the formulations shown here, as if we rewrite this update rule, shown in green, we can see that it is the same as the update rule with weight decay. Because of this equivalence, most deep learning frameworks only implement the L2 regularization. However, there are two issues with that. Firstly, under Adam optimization, weight decay and L2 regularization are not equivalent. And secondly, using L2 regularization with adaptive learning rate optimizers like Adam may lead to very large learning rates, which causes convergence issues. Therefore, when you are using adaptive learning rate methods for training, it's best to use weight decay instead of L2 regularization. That's where AdamW comes in to modify the update rule for incorporating weight decay regularization in Adam. Most of the steps, such as estimates of the first moment MT and the second moment VT and applying the bias correction, are the same. The only difference is the highlighted part in the update equation, where we will add the weight decay term lambda times the previous parameter w sub t minus 1. And that's all we have to do. Pretty simple modification, but effective for regularization. So as a take-home message, remember to not use L2 regularization with Adam, since it may lead to extreme learning rates. Instead, use AdamW. Hi everyone. The next optimizer, Yogi, is another extension of Adam that is proposed to address the convergence issues, especially in non-convex stochastic optimization problems. Yogi uses the same estimate of first moment as in Adam, but for the second moment estimate, Yogi adds a factor that is sine of v sub t minus 1 minus the squared gradients. And the rest, including the bias correction and the update rule, are the same. So to understand how this modification affects the estimate of the second moment, let's take a look at the change in v sub t minus v sub t minus 1 and see how they are different between Adam and Yogi. As you can see here, in both cases, when a squared g sub t is greater than the previous estimate of the second moment, this quantity Vt minus 1 minus a squared G sub t will be negative, and it results in increasing V sub t in both Adam and Yogi. However, in Adam, the magnitude of the change depends on both V sub t minus 1 and G sub t. But in Yogi, the magnitude of the change only depends on the current gradients, not the past V sub t minus 1. So this makes Yogi to have more controlled change in the effective learning rates. Hi everyone. And finally, our last optimizer in this family is called Nadam. Nadam is an extension for enhancing Adam Optimizer with the improved gradients, or as they are called, the Nestrov accelerated gradients. For Nadam, the second moment estimate and its bias correction are the same as in the original Adam, but the first moment in Nadam undergoes a different operation. If you recall, Nestrov momentum performs a partial update before computing the gradients at step t. Here with Nadam, when performing bias correction for the first moment, we also include the current gradients G sub t, as it is shown in this equation. The gray box is displayed for comparison purposes, showing the bias correction of the first moment in the original Adam. So that brings us to the end of Adam family of optimizers. And for our last category, we have the Lookahead Optimizers, an optimization algorithm that is orthogonal to all the previous optimizers we have seen in this video. Lookahead Optimizers keep two copies of network parameters, which are called fast weights denoted by theta and slow weights denoted by W. Fast weights are updated using an optimizer in an inner loop k times, and you can choose any of the previous methods such as SGD or Adam. After performing k updates on fast weights, then they use the latest state of the fast weights to update the slow weights in an outer loop. Let's see how the inner update and the outer update work. Assume algorithm A is chosen for the inner updates, and also note that we use two subscripts for theta. Theta sub t, I, where t is the global step and I is the iteration of the inner loop. Before starting the inner loop, we first synchronize the fast weights and the slow weights by assigning theta t, 0 to be equal to the latest state of slow weights, which is W sub t minus 1. Then, in each iteration of the inner loop, we first take a random mini batch of data and make an update on the fast weights theta using the inner optimizer A. We can repeat this process of sampling a mini batch and making updates k times until we get theta sub t, k. After the inner loop runs out, then we update the slow weights using the last state of theta as shown in the right. So we update the slow weights W in the direction of change going from Wt-1 to theta t, k. So that's all for the Lookahead algorithm. This is a very effective optimization technique. It just needs a little extra memory for the two copies of the model weights and some negligible extra computation. But on the other hand, it improves the learning stability and decreases the variance of the inner optimizer. Hi everyone. So we covered 16 different optimization algorithms for training neural network models. Also, if you want to have further readings on these topics, feel free to check out the description of the video. I have made the references for the optimizers covered in this video available in the description. I hope you find this video useful, and thanks for watching.